Okay, so we have a conceptual understanding of water potential now. And now what we're going to look at is how do we actually calculate water potential using the water potential equation. So here's the water potential equation. It's equal to the pressure potential plus the solute potential. And we'll see how we determine each of these individually. Something to note first, the pressure potential will always have to be given to you. They will have to tell you the pressure is blank. Let's say the pressure is zero point 0.5. They'll have to tell you that. The solute potential is the only one that you'll be responsible for calculating. But we're going to look at how do we understand the pressure and solute potential before we keep going. Okay, so here we have an open container, and in an open container, you actually cannot build up pressure. So even if you were to pour more water into this container, eventually it would just overflow. You wouldn't build up pressure. So the pressure potential there would be equal to zero. So again, we can pretty much ignore pressure potential because our equation again is water potential equals pressure potential plus the solute potential. So in an open container, we just need to worry about the solute potential, which we'll get into in a second. The same is true in an animal cell. From our last video, we talked about in an animal cell, because it just has a cell membrane, if water flows into the cell, yes, it will create some kind of pressure in there, just as if you fill up a water balloon. However, eventually that pressure is going to lead to the cell exploding. So I'm going to just show the cell here in the next stage. So eventually that cell is just going to explode because it can't hold that pressure. So the pressure potential in an animal cell will also be equal to zero, and we can ignore it in our equation. So then what about in a plant cell? So in plant cells, a reminder that plant cells have a rigid cell wall in addition to their cell membrane, which we can see in red. So in a plant cell, if water moves into the cell, unlike the animal cell, the plant cell can actually hold pressure. It's not, the cells are not going to explode. So in this case, if water is moving into the cell, you're going to create a positive pressure potential. This would be a scenario where in a problem, they would have to say the pressure potential is equal to some number other than zero. Okay. So then what about when we're talking about solute potential? So what about solute potential? So if I add solute to something, so if I dissolve something in water, so here we can see some water molecules shown in red and white. If I add something, let's say I have a cup of water and I add sugar to it, or I have a cup of water and I pour some salt into it. I stir that with a spoon and it dissolves. How does that happen? How does it affect water potential and solute potential? Well, let's take a look. So in this case, let me first clear these out. So in this case, we have water, which we can see shown in red and white here. And remember that water, the oxygen has a slightly negative charge, and the hydrogens have slightly positive charge. And so that's going to result in things like hydrogen bonding. So there's hydrogen bonds that are happening between these adjacent water molecules. But it also affects water's ability to dissolve substances. So if we look at the picture on the left, we can see that some of these water molecules are surrounding these solutes. So these are those positive and negatives you see are those are solutes that are dissolved in this water. So maybe that's salt, for example. And we can see that based on the charges of water, so here we have positively charged, pause for a second. So here we have positively charged hydrogens that are surrounding these negatively charged solutes, and we have the negatively charged oxygen surrounding the positively charged solutes. And the way to think about this is when these water molecules are surrounding these solutes, there's only some of them that are left that are able to go dissolve other substances. This is why the solute potential becomes more negative because there is less or there are fewer free water molecules to go dissolve other things. Versus in a hypotonic solution or in this solution that doesn't have anything dissolved in it, there's a lot more water molecules that are ready to go do dissolving of other substances. So how can we use this in this situation? So using all of that understanding, we know that we have pure water, so that means there's nothing dissolved in it. So pure water is going to have no solute. So the solute potential is going to be equal to zero. and it's in an open container, so there's no pressure potential building up, and so there's equal to zero. And so here, water potential of pure water in an open container is equal to zero. Okay. So by and large, water potential is we're going to be able to ignore the pressure potential because most of the time it will either have to give it to you or we can ignore it because it'll be in an open container or an animal cell. So then most of the time we have to calculate the solute potential. And here's the equation that will be given to you, and each of these units will be given to you as well. And so how do we calculate solute potential from here? Well, first let's break down each of these terms. So we'll start with the two that you don't ever have to calculate. They'll be given to you. So one is the unit R, which is the pressure constant. This number will always be given to you on your equation sheet. All you have to do is take that number and plug it in to the equation. The next one is the molar concentration. We'll get into that in more in a second, but the molar concentration will have to be given to you. We'll get into the units of that. It will be given to you. All you have to do is plug that in. The next one, temperature and ionization constant, get a little tricky. But one thing I forgot to point out is there is a negative sign in front. That's going to be super important when we start doing these calculations. Okay, so let's break down the ionization constant, or I. So how do we figure this out? So this will not be explicitly given to you, but it will be one of these two options. So it's either going to be sugar or sucrose. Let me use a different color so it sticks out a little better. So it'll either be sucrose or some type of sugar, fructose, galactose. It could be any type of sugar. And sucrose will always be given an ionization constant of 1 because it doesn't ionize in water. Now, more on that in a second. Versus if it's salt or NaCl, it's going to have an ionization constant of 2 because NaCl, when you dissolve salt into water, the positive sodium ion and the negative chloride ion are going to ionize, or they're going to separate into two separate ions like we saw in that diagram of water. Let's see a better picture of that here. So in this diagram, you can see here's salt shown in the green and purple. And when you put water molecules around it, again, thinking about those negative, those partial negative and partial positive charges, you're going to see that the sodium is split apart from the chloride and the chloride is split apart from the sodium. And that's how it goes about dissolving. So there's two ions. That's why the ionization constant is 2. When you dissolve sugar or any type of sugar into water, it does not get ionized. It stays as one big molecule. So that is why sugar or sucrose or any of these sugars have an ionization constant of 1, and salt has an ionization constant of 2. Okay. Now, what about these substances here? So what about the molecular compound work? So this will be something that has to be given to you. You won't have to calculate it. It's given in the units of molarity, or in this case, moles per liter. And we can see an example here, right? So here's two solutions. They actually have, if you counted the yellow dots, you could pause it and count the yellow dots. They have the same number of solute molecules that are dissolved in it, but there's a lot more water in this compared to this. So in this case, there's going to be a very low, this will be a low concentration versus this is going to be highly concentrated. So if this was salt, this would be really salty water. It would taste really salty versus this water would not taste that salty because there's so much water to balance out the salt. Okay. The pressure constant we talked about, all you have to do is plug that into the equation. It's going to be given to you. What about temperature? So it says this on the equation sheet too. The temperature will most likely be given to you in Celsius, and you have to convert it because this formula uses Kelvin. So to convert from Celsius to Kelvin, you have to add 273. If you wanted to try it, you could try it here. So you'd have, what's the room temperature is about 20 degrees Celsius. What would this be in Kelvin? I add 273 to it and I get 293. And I would go plug that into my equation. Okay, so let's see an example of solving this. So how would I solve this question? So let me go back here. So solving this question, I can see in our example, it says you create a salt solution. So, okay, I'm thinking salt. What does that mean? Maybe pause the video. Think about what is salt? What's the significance of that when I'm calculating water potential? We have a molar concentration, right? Moles per liter. It's given to us. We have a temperature of 22 degrees Celsius. Calculate the water potential for this solution. First off, I know that my water potential equation is equal to the pressure potential plus the solute potential. There is no pressure that's given to us. We can assume this is an open container. We're going to ignore the pressure potential. We're going to assume it's zero. So now we need to calculate the solute potential to be able to figure out our water potential. So let's see how they did that. So first, we're going to plug in our I. We have to find I. So what is I? That's the ionization constant. Because we're talking about salt, it's going to split into two ions, sodium and chloride. So my ionization constant, or I, should be 2. Notice the negative sign has to still be there. Okay. My molar concentration, don't have to do anything with that. That's my letter C, is going to be equal to 0.15. The R has to be given to us on your equation sheet, which it will be. And there it is. I plug it in, 0.0831. And then last is my temperature. Remember, you have to first convert the temperature to Kelvin. So I take 22 and I add 273 to convert to Kelvin, and I can plug that number in. And here is my water potential for this solution, negative 7.35. Okay, hopefully this video was helpful, and we'll see you in the next one.